All right, people. Hey, sorry I'm not here on the first day of the trimester. I know that's probably a little annoying, but we're still going to be able to get through what we need to here today. Today, you should have gotten a note sheet and a packet from Miss Jen. We're going to start out on this note sheet. We're looking at 6.1. We'll fill out most of the stuff there on the front page. 6.1 is about exponential growth and decay functions. Now, you've looked at exponential growth and decay before in Algebra 1. Most of what you're going to see here is a review. Even though I know it's been a while since you've seen these things, it is something that's been in front of your eyeballs before. Now, exponential functions in general take this form. Y equals A times B up to the x. And x being in the exponent is the thing that makes it exponential. Remember, exponential growth would look like this. Exponential decay would look more like this. This A value is always going to be our starting amount, our initial amount. When we deal with money, we call that our principal. This B is whatever we are multiplying by. And there's more to it that goes into it than just that, but we're going to look at that here through these slides. Now, exponential growth, there's nothing you need to write on your note sheet quite yet. It'll be super clear when you need to. Exponential growth breaks down that B value and says, okay, if we're going to be growing, that means that these points have to be going up. So whatever that B value is, whatever we're multiplying by has to be greater than 1. So we break down that B value to say it's 1 plus R. This R is our rate, and it's raised to the T, which is time. If we're dealing with something that's decaying, something that's going down, well, that means that we have to be multiplying by something smaller than 1. So we say whatever our rate is, whatever percent we're going down by, we do 1 minus that rate in order to get our B value. So both of these are still representing an exponential, A times B to the x, but we're just breaking that B value down differently if we're talking about growth or decay. Now let's look at the two things. Here we're looking at your notes at the first exponential growth on the left-hand side. Here's the example. We start out with 3 bacteria, and the amount of bacteria increases by 75% each minute. If we had to write an equation, we'd say, okay, it's increasing, so we know that that would be exponential growth. My initial amount, is 3 bacteria. And I have 1 plus, I have to write that percent as a decimal. X or T, most of the time I put T, but sometimes I forget and write X. But it'd be the same thing up there. My initial amount would be 3. My growth factor would be 1.75 when I simplify these parentheses. This is my rate. Here's my growth factor. My percent increase is 75%. If I were to ask you to sketch just a little graph, we'd have a y-intercept at 3 and we'd be going up. We don't do a ton of graphing here in this chapter. Some, but not a ton. I kind of already converted to this y equals A times 1 plus R to the T. That's what we have right up here. Now, on the other hand, if we had exponential decay, the equation exponential decay is 1 minus R to the T. Well, my initial amount is $100, and I'm losing 8%. I've got to move that decimal place twice. My initial amount is $100. My decay factor, the number in parentheses, would be 0.92. My percent decrease is 8%. Whoops, there we go. In my graph, my y-intercept would be way up at 100, but it would be decreasing. It would be going down like this. And again, I already wrote this right up here. So you can see it's pretty clear. They're going to say you lose money, you're gaining money. It's going to be pretty clear what's happening if it's growth or decay. You just need to make sure you write that percent as a decimal and do 1 plus that percent or 1 minus. Now, continuing on with a couple other things with exponential growth or decay, and just with these exponents in general that we're going to see. This would be the under the convert y equals a times 1 plus r to the t, there's another example line. This is where you can put it. The example is y equals 2 times 3 to the 1/4 t. Now, sometimes they're going to give you these equations, and they're going to put a number up here with the exponent. The problem with this is we can't convert to this form if there's a number up here, okay? It leads astray. It doesn't accurately show what our r value is. So before we can do anything here, before we can work with an equation like this, we first have to type into our calculator whatever 3 to the 1/4 power is. I got 1.32. Now this equation is in a form that I can work with. If it asks me to convert it, great, I can do that. If it asks me for my rate of growth, same thing, no problem, I can do that. It's 32%. So let's look at another example. If I gave you y equals, let's say I had 15, 0.95 to the 1/4 again, t. This equation is not yet in a form that I can work with. I've got something up in the exponent with t. So the first thing that I need to do is do 0.95 to the 1/4. Now this equation is in a form that I can work with. If I need to write it as 1 minus my rate, it would have to look like this. This can be a little bit tricky. 1 minus, a lot of people get tricked and just write 0.987. But if I were to do 1 minus, I need to get, when I do 1 minus r, this is the number that I need to get. So 1 minus r needs to give me 0.987. If I solve to get r by itself, this is what I would get. This is my r value. That's something we'll talk about more. You'll practice more and more, but for right now, I'm just going to leave you with that example. Now I think we've got 3 quick examples here. I'm going to talk through these. We'll solve pieces of it, but I don't want this video to get too long. So I'll more talk about these questions. We might not type out the answer to every single one. The value of a car can be approximated by this model, where t is the number of years since it was new. Tell whether the model represents growth or decay. Well, my number in parentheses is less than 1, so I know that this is decay. Identify the annual percent of increase or decrease. It's decreasing. Now, like I said, the annual percent decrease, that's another way of asking for my r value. I got the 0.85 by doing 1 minus r. So 1 minus r equals 0.85. I have to solve for r. If I solve for r, I get 0.15. It asks for the percent, so that would be 15%. Estimate when the value of the car will be $8,000. So that's asking me to set my equation equal to 8,000. And I'm not going to go through this in this video here, but the next thing I would do is go to my table. I would need to see when my y value is about 8,000. Whatever my x is, let's say it's at, I'm not going to use 8, let's say it's at 10, and it's $8,111. Well, then I could say, okay, it's about $8,000 after 10 years. That's how much it's worth. The world population was about 6.09 billion. During the next 13 years, the world population increased. Now we're going up 1 plus r by 1.18% each year. Write an exponential model giving the population for years after 2000. So I need to just change my rate to a percent, 0.018 to the t. And I would expect you to add those together. Like, we're not going to leave our answer with the plus sign here, 1.018 to the t. It says estimate the world population in 2005. Well, this was through 2000. If the trend continues, that just means I need to plug a 5 in for t. Estimate the year when the population was 7 billion. So if I need to estimate when the population will get to 7 billion, I put t, I put this into my y equals with a t up here. And again, I'm just looking in my y for when this equals 7. Compound interest is the formula that's towards the bottom of that paper. We're going to save this for tomorrow. So I'm not going to cross it out, but we're going to save for tomorrow. You've got a few things that you need to look at in Canvas. Don't worry, if you have questions, I mean, I'm not going to keep you lost after the first day, especially with me not being here. So if you have questions, we'll catch you up tomorrow. But otherwise, do the best you can on those homework assignments.